general relativity, step by step. I've got these two geodesic curves here for two neighbouring particles which are cruising along geodesic curves together. And I guess it boils down to this thing here. I need to evaluate alpha mu, the Christoffel symbol, evaluated at x bar alpha, where x bar alpha equals x alpha with no bar plus my separation vector n. Well, what's that? Well, that's at mu nu evaluated at x alpha plus n alpha, which equals just the regular one, alpha mu nu, evaluated at x. I'll call it alpha. Maybe I should have a different. Oh yeah, I'll call it alpha. It's not this. It's not summed. Just at x, I guess. Just at x. Just at x. Point x. There it is. Plus. Now let me get this right. It's n sigma di Christoffel symbol alpha mu nu by di x sigma, summed over sigma, of course. So there's the relationship, plus higher order terms, I guess, but we're assuming that this n separation vector is small. Okay, well that means that I can start to substitute into my geodesic equation. So let's have a look at that. Well, here's my equations here, and of course what I want to do is to get rid of all, I want to expunge all bars from my coordinate system and just do it in terms of n, the separation vector, in just the same way that when I was fooling around with the Newtonian case, I actually fell with these particles into the black hole so I could observe their relative acceleration, which is what I call tidal functions, tidal forces. Okay, well let's do that. Let's just dear, quite a lot of algebra here. Never mind. Let's just have a look. Okay. Well, let's start out with that term there. I'm going to run out of space, aren't I? Let's do it a bit. Let's pinch in a little bit. That's going to be d2x alpha plus n alpha by d tau squared plus, well, I guess I can substitute for this guy in already because I've got the equation here. Here's the Christoffel symbol evaluated here, but I can get rid of the bar just by using this substitution formula here, and then using the fact that n is small. Mu nu plus n sigma di, I'm just copying from here, alpha mu nu by di x sigma. That's my Christoffel symbol, that's this thing here, times, d by d tau of, instead of x bar mu, I'm just going to write x mu plus n mu, times d by d tau of x nu plus n nu. Good grief. What does this equal? It's a geodesic, so it's equal to 0. Good grief. Stop there. Okay, so that's the geodesic equation for the second of the two particles. That's this one here. My reference particle's cruising along here, and this one's got a separation n. So what I can do is to write down the equation for the reference particle here, and then I'll just subtract that off. I guess that's the essence of calculus. So I've got d2x alpha by d tau squared, plus, all I'm doing is writing this equation here down, and I'm going to subtract off the terms. Alpha mu nu dx mu by d tau dx nu by d tau equals 0. And I'm going to subtract one equation from the other and see what happens. Well, I'm not going to subtract them exactly. Well, I am going to subtract them, but I'm going to use the fact that n is small. You'll notice I've casually used the fact that n is small because I'm talking about relative velocities at two different positions in space-time. So I'm implicitly using that fact anyway. Right, so what have we got left? We've got d2, this term here is n alpha by d tau squared, plus right, okay, let's have another bash at this. We've got Christoffel symbol here, alpha mu nu times, I can't have two n's multiplied together, but I can have a dx mu by d tau for this one, and an n nu dn nu by d tau for that one, plus, and then the other way around, alpha mu nu dn nu by d tau dx, oh no, that's a mu, x nu by d tau. Ha, and of course those two are the same. That's quite nice. Plus this term here, n sigma di lambda, Christoffel symbol, alpha mu nu by di x sigma, summed over sigma. Now I've already got an n here, so I can't have another one because that's the second order term. We've got to have dx mu by d tau dx nu by d tau equals 0. Good grief. Good grief. Let me just combine some terms. d2n alpha by d tau squared plus 2 Christoffel alpha mu nu. You see they just swap over. dx, which way around shall I do it? dx mu by d tau d n nu by d, is that a t or that's a tau? Yeah, those two terms are the same because the Christoffel symbol is symmetric. So that's that term and that term done. I've got this one here, plus this last one here. N sigma di by di x sigma of Christoffel symbol alpha mu nu times dx mu by d tau dx nu by d tau, and that equals 0. Now I can still simplify this a little bit more. I can say that's d2n alpha by d tau squared plus 2 Christoffel alpha mu nu times u mu, because that thing there is just the velocity of my particle, the fore velocity at least of my particle, times dn, let's leave that as a nu d tau, 2 of those, oh I've got the 2 there, look, plus the other term, n sigma di Christoffel alpha mu nu, just copying from here, by di x sigma, and then I've got an x mu by di tau, so this is just, that's just u mu u nu, and that equals 0. Whew! I think it's time to stop. That's quite a nice equation. So what this is doing is giving me a differential equation for n, which equals the separation vector between my two world lines of my two closely separated particles as a function of proper time tau. And the whole problem was, or the difficult part was, accounting for the fact that the curvature of space is different from point to point. So we had to use a Taylor expansion for the Christoffel symbol. But we've got this rather nice equation here, which I'm going to play with, and I'm going to use it in the next screencast. So I'm going to stop there. Stop.